So, Vanakkam. So, we will continue our lecture on engineering seismology. So, today we are going to talk about the ground motion simulation models. So, the ground motion means basically, as we have discussed in the previous class, the time history data, okay, acceleration versus the time. The plot of the earthquake is called as a ground motion data. So, this data basically you need to be recorded during the earthquake. As we have seen that the seismic instrumentation itself developed on 1880. Okay, then in India the first seismic instrument was installed only after the big Shillong earthquake. Okay, so by considering that, we have seen also the up to 1960 there is not much seismic instrument in the country, and initially there was a many analog instruments was there, then followed by those analog instruments are basically shifted to the digital instrument. Now we have reasonably instrumented this one, but unfortunately there are many big earthquake which was reported earlier in the last century and even before 40 decade and 30 decades. Okay, but we do not have recorded acceleration time history data. Okay, if you want to do analysis, okay, so like we have seen that time history and response spectrum and tripartite. So, there are two type of structural analysis people will do. So, one is they do a time history analysis. Time history analysis means they take a structural system, model that complete structure in the computer and apply a typical recorded earthquake as a time history data. Just they apply that and then see and how the displacement varies at different places for the given structural configuration, and then if they needed they will basically modify that and see that it is safe and does not cause a failure or a collapse or the more displacement. That is what they do. That kind of analysis called as a time history analysis. So, you take a typical earthquake data and give us directly input. Okay. So, that is the one way. The another way is people take a spectral values. We have seen the design spectrum last time. No? They take that spectral value and design a structures. Okay. So, which is like a simplified way of the time history analysis, because the time history analysis you need very complicated computer modeling software as well as a computing facilities. In the response spectrum analysis you no need like that. Okay. You can even do a hand calculations or Excel based calculation kind of thing. So, this is the way structural people design a structures. So, as I said that the old earthquakes are not available and recorded data is not there. So, then how do you design? So, that is the way the designing requirement to fulfill those kind of requirement, scientists come up with the idea called a ground motion simulation model. So, that means whatever the earthquake physics you are understand, how the earthquake mechanisms all you understand, that modeling, okay, you solve that equation, okay, then you will get your acceleration time history data at a particular place. So, generally the simulation models most of the time develop a S wave portion of the earthquake, not the P wave and the surface wave, as this does not cause too much damage to the structure, which we have seen during the wave propagation. So, today class we are going to talk about the earthquake simulation model basically. Okay. So, we are going to talk about a earthquake simulation model. So, which will help you basically to simulate synthetic ground motion of the any record data. So, the simulation model, okay, the simple and powerful method for simulating the ground motion by modeling a event, okay, the earthquake event as a random phase spectrum modified such that the motion is distributed over a duration related to earthquake magnitude and distance from the source. You can see that the simulation model, the main parameters is actually the earthquake magnitude and distance from the your origin of the earthquake. So, if you take a random phase spectrum, which we have discussed what is the phase spectrum during the frequency domain parameters, and you can even Google it and read about if you want to know what is the phase spectrum. Okay. So, by making a phase spectrum. So, by splitting the recorded ground motion into characteristics source, path and site, that modeling of each of these by their functional form will become easy to understand how its model. So, this is the typical earthquake. So, occurring in the generally. So, this is where you are looking at a design of the ground motion. So, this is the hill and this one. So, this is where basically a source. So, this is the source So, this is basically so this is where you can see a source. This is the one which is where earthquake is origin, the fault is rupturing. As I said that the waves are getting travelled like this. So, when it reaches a engineering bedrock, you can see this is the engineering bedrock. So, the wave which travels very long distance from the parent source to the engineering bedrock, that is called as a seismic bedrock. So, this is will have roughly the velocity of 3 kilometer per second to around up to 1000 or 1200 or less than 1000 kilometer per second up to this phase. Then followed by you will have the soil. This soil velocity will be always less than 760 meter per second. This thickness varies, depends upon the place to place. So, that means the entire process, okay, what we deal actually can be grouped as a 3 category. One is the source characteristics, which is taking into the account of, so which is taking into account of your source what happens. Okay, so this place what happens is the source characteristics. The second is the path characteristics. The another one is the site characteristics. So, by solving what happens here, what we understand the attenuation characteristics, seismic moment, corner frequency, cutoff frequency. So, by solving all these equations separately and clubbing together, you can get what is the a typical event waveform look like in the surface. That is what the simulation model does basically. So, this motion mostly, okay, simulated for the S wave component and predominantly for the rock site condition, as the soil conditions are varies location to location. Okay, as you might have seen you that. So, in your house the soil found in that place may be different depth and different thickness and different type, and if you go little 50 meter 100 meter away, you will have again a different depth, different soil type kind of thing. So, the modeling of site characteristics is not so effective. People only concentrate up to the modeling at engineering bedrock level. So, this is the level they try to model the your simulations. So, this simulation, ground motion simulation models has a great advantage, as I told you that. So, used for simulation of ground motions in the absence of the recorded data in the region, very useful for development of ground motion prediction equation, which we will be discussing what is the ground motion prediction equation in the later stage. Useful for seismic hazard and site response and liquefaction studies at the site with no recorded available data. Okay, so, it is also used for the seismic hazard, site response, liquefaction, where there is no recorded data is available, and can generate a ground motion with frequency in the range of natural frequency of structures. So, since it is simulation one, you can only generate a frequency where your structure is important. Okay, for example, more than 1 hertz. Okay, so no, so less than 1 hertz, something like that. Can simulate earthquake as bigger as magnitude 12 in any kind of tectonic region. As we have seen that so far the maximum reported magnitude in the world was actually 9.7. Okay. So, if you want to go higher magnitude, the only simulation is possible. Okay. So, hence can be used to seismic hazard region and designing the very important structures, and then simulation of the earthquake in the seismic gaps or the expected area of the earthquake. As I was telling that there may be a main shock of the earthquake which you can expect in the Delhi region, because there is a force shock. So, if you want to simulate estimate what is the magnitude expected there, and you can simulate that earthquake and try to understand if that earthquake comes, what happens to the different part of Delhi. So, those kind of studies are need this kind of simulation. So, what is the limitation of these ground motion models? Basically need number of regional parameters to model, because depends upon the input parameters. Okay, so your acceleration time history changes. If you assume so many parameters which is not measured in the your region, you will end up in the wrong acceleration time history. Okay. Then the parameter can be obtained from the recorded data, then it will more reliable. In the absence of regional recorded data means not a big earthquake, even a minor earthquake, you will give the your cutoff, corner, and then the seismic moment. Okay, so then the attenuation characters, all those things you can be obtained even a minor earthquake data. So, the evaluation and regional parameters, all those things will be in the absence of recorded data, evaluating these representative regional parameters are difficult. Okay. Other parameters such as a fault plane solution, rupture initiation need to be known are assumed for the efficient simulation, which is not really available. So, the recorded data will give you some type like this attenuation characteristics, corner frequency, cutoff frequency, where you can also estimate a seismic moment by knowing the corner cutoff frequencies and also by knowing the expected magnitude. But the fault plane solution, what type of fault it is. If there is no big earthquake in that particular fault, it may be difficult to get a fault plane solution. Second, where it rupture start and how it initiate, how it propagates. So, that data also difficult. So, these informations if you assume without detailed this kind of information, you will be ending up in the wrong simulation of the ground motion data. So, anyway, as on now, this is the only way you can get a simulation data. As much as possible, we will try to get a regional source and path parameters. So, recently we have done this kind of parameter development and also simulation large extent and developed a ground motion prediction equation. So, if time permits, we will be discussing one class how we have done, what we have done, what are the equations is available in the later stage. So, what the Bohr done 1983, you can see the model when it was developed just about less than 40 years back. So, the Bohr who is the USGS seismologist, well known world famous seismologist, so even I do have some interaction with him. So, said that the total spectrum of ground motion recorded at any site is the function of combined features of source, path and site characteristics. This is what we understand. So, this is the ground motion at any particular site. So, any particular site. So, any particular site is the function of source, path and site. So, as we have seen that the source is controlled by the seismic moment and frequency. The seismic moment is m naught is the seismic moment which is directly related to the magnitude of the earthquake. So, this is what we have seen. So, the the source so the source effect the energy at source equal to the function of seismic moment and m equal to C m naught s into m of f. So, the C actually is depends upon this, which is basically r naught is the reference distance. So, so the rho V is the partitioning energy into the two horizontal direction, and then this r the factors is radiation factor averaged over your entire azimuth. The beta is average shear wave velocity of the crystal rock. So, this is the velocity at where the source going to rupture. F is the free surface amplification, rho is the density. So, by knowing this, you can solve this equation and you can get a source the related the wave part. So, then the next is the propagation path. So, the path effect should be account geometric spreading, attenuation effect and increase of duration motion due to the propagation waves they are spreading. As we have seen that when the waves are travelling on the very long distance, you will have the long duration. So, that has to be accounted here. So, the path effect P is the function of r and f. R is the distance from the site, preferably it is a hypocentral distance, is the ZR exponential of pi f r into q of f and CQ. So, here the ZR is basically the geometric spreading function and it is a regional parameter, can be estimated from the minor recorded earthquake in the region. QF is the quality factor account for attenuation characteristics. Attenuation characteristic ground motion, particularly high frequency ground motion. It can be also obtained from the linear slope of the frequency spectra between the corner frequency and frequency of the interest. The QF can be obtained like that using the regional data. CQ is the seismic velocity used to determine the quality factor. R is the shortest distance between the rupture and the site. So, the distance depends upon duration and ground motion is sum of source duration, which is inversely proportional to the corner frequency and path dependent duration. So, there are number of correlations are available, but you should see that these correlations are applicable to your region, depends upon the seismotectonic and the regional attenuation characteristics which is arrived from the minor earthquake. This is what a path duration. The site effect generally counted a local geology at a site, it is difficult to explore very correctly, as I discussed earlier. The simulating of ground motion using the stochastic process involves a prediction of the motion at a generic site such as a bedrock condition. So, most of the time the simulation they do for the bedrock condition, not for the soil condition. So, because of that the site effect study is not much addressed in this simulation model. So, in such case site effect GF can be further decomposed into a local site effect and amplification and attenuation between the bedrock and the engineering bedrock. So, here the seismic bedrock, engineering bedrock attenuation, what happens. So, the GF is amplification and DF, the factor which attenuates. The AF is the square root of the impedance ratio at the source and the site. So, which you can obtain from like this, the amplification factor. The ZS is the seismic impedance. So, the ZS is rho into BS. BS is basically the density shear wave velocity of the respectively at the source and a different medium. ZF average nearly impedance ratio over a depth equal to quarter length, usually 100 meter below the surface. So, using this you can get a AF. So, the diminution fact operator DF, it accounts a path dependent loss of I energy ground motion. It can be modeled using this function, where the factor K accounts the high frequency ground motion alter between the crystal rock and the engineering bedrock. Factor K can be obtained by normalizing the Fourier spectrum beyond the corner frequency. The simulation can be so these steps whatever we discussed in detail can be clubbed as a 6 simple step. One is that generating a first weight noise equal to the duration of the motion obtained from the corner frequency, and then filter the noise by applying a Gaussian window, convert the window noise to the frequency domain by fast Fourier transformation, and normalize by obtaining the Fourier spectrum with the square root of mean squared average spectrum, then the normalized spectrum, then multiply the ground motion spectrum, again convert acceleration time velocity domain by the inverse Fourier transformation, then you will get a acceleration time velocity. So, you can see that, as I told you during the frequency domain parameters, the parameters we discuss in the frequency section basically helps in the simulation part predominantly. That is why you can see corner frequency, cutoff frequency, then the Fourier spectrum, normalizing the Fourier spectrum. So, all those things parameters are very useful in the simulation. So, simulation of the ground motion itself a PhD topic. So, one can work on simulation of the ground motion for one region and try to get a different ground motion, get a ground motion prediction equation. That is the PhD topic in the reputed institute. There are very few ground motion simulation and GMP developed in India so far. So, this is that 6 steps has been broadly explained pictorial way. So, this is basically a noise which is simulated based on the duration. Then apply a Gaussian window noise filtering. So, then you will get a this was as it become like this. Then model a spectrum. You can, this is the spectrum you will get, which is taking into account of your corner frequency, all those things. Then the Fourier amplitude of the same window you can get here. Then normalized spectral amplitude you get. From this you get a acceleration time velocity by again the inverse Fourier transformation. So, this data is basically your required ground motion simulation data. This is what you do at the end of the simulation. Even though I explained this the entire step in the last 10 minutes, but it is very complicated mathematical modeling work. So, very few people actually contributed to development of the models. So, most of them are only using that model using the regional data. So, for example, in the world so far only there are one simulation model which is primarily developed, later it has been modified. So far nobody developed independent simulation model other than Bohr. Rest of them are developed and modified the Bohr model and called as a different model name, which we will be discussing followed by this slide class. So, right now India people only use those models, simulated models which is freely available in the website, and try to simulate for the different distance and m. Some people use a regional parameter, some people does not even consider regional parameter, they use model input parameters or example parameters and end up in the some kind of acceleration time velocity data, which may be relevant, may not be relevant, depends upon the input given in the particular location. So, the stochastic simulation, the approaches the new simulation of ground motion filter and window white noise time series according to the seismological determination of average spectrum and duration. The stochastic simulation point source model. Okay, so, earthquakes are engineering approach by simulation of ground motion, which was developed by the Bohr in 1983. The stochastic simulation strong ground motions that relies on the seismic source physics has found substantial application in the earthquake engineering with a successful comparison of the predicted and recorded data. So, Bohr developed this stochastic simulation model, and he found there is a good application in the engineering seismology. He also validated his model by comparing the really recorded earthquake from the simulated earthquake. So, the Bohr updated his model again 2000, developed so called band limit white noise model for stochastic simulation of the ground motion. So, with a seismological constraint. Okay. So, these simplified models, okay, so there are three type of ground motion simulation models are available. So, one is the point source model, which was the origin for the rest of the other two model. So, it was developed by 1983 Bohr, which is called as a SMSIM, SMSIM, okay, SMSIM model. So, SMSIM model. The another one is that model actually further modified by the Brenau and Atkinson. They call it as a finite, okay, so fault finite model, which is called as a FINSIM. Okay, it is developed on 1997. The finite point model simulation model again modified by the Motosidia and Atkinson. So, that model is called as a EXSIM. So, these are all the three different simulation model which is widely available in the world, and people use to simulate a ground motion data. We will discuss these models and its advantage and limitation, what are the input needed in the now. So, the SMSIM, okay, model was developed by Bohr in 1983. The earthquake ground motion will be treated as a rupture at a single point. So, he treat that as a point source. Okay. So, modeled as a white noise window using the Gaussian window similar to the steps given earlier, useful to simulating the ground motion at a distance much larger than the rupture dimension. So, this will be the rupture dimension should be smaller and the distance where you simulate will be larger. It cannot capture a rupture directivity, cannot capture rupture heterogeneity, cannot capture the fault geometry. So, these are all the limitation of this model. So, that means you can simulate this kind of earthquake for the smaller magnitude where this effect not much noticed. Smaller means magnitude of 7 and less, as we have discussed in the simple model we have found 5, no. So, that was a very simple model. So, this is slightly complicated model, it works up to magnitude of 7. People have done with the different cases and compared and reported that. So, then another one is the FINSIM model. So, the FINSIM model actually developed by the Breslau and Atkinson 1997. As I say, the entire rupture area will be divided into number of subfault. Okay, so, they take the entire area and each subfault will be treated as a single point. So, here instead of one single point simulation by the Bohr, these people divide the area rupture area as this one, and then model each segment as a point source and with omega square spectrum. Contribute from each subfault will be summed up and sufficiently delayed depending upon the rupture velocity and subfault size. Then finally, they arrive here total slip, total ground motions from these small things. So, useful to estimate total slip distribution of the rupture area to understand directivity effect of the accurately. Okay, so, prematuration have been performed. So, this has a this directivity and then the slip distribution can be easily. The limitation is simulation needs lot of regional parameters such as a strike, we know what is a strike, slip, dip, stress drop, rupture area, geometric spreading, kappa factor and strength factor. So, this kappa strength, okay, so you can get from the recorded minor earthquake recorded in the region. Okay, so, the geometry spreading should be have from the previous past earthquake data, So in case if it's not there, it is a problem. Rupture area, again you should have the rupture dimension versus the different magnitude occurred in the region. So right now overall in the world only very few equations are available with respect to rupture area. Stress drop, you should we have discussed that before and after earthquake, what was the drop of stress. Okay, that is again depends upon the region, which has to be obtained for different magnitude level. So the fault parameters, strike, dip and slip, this you can get by doing the deep geophysical survey. So if you do a deep geophysical survey, you can get. So this kind of many complicated parameters are required in the FINSIM model. So such parameters are difficult to obtain in the absence of larger number of regional record. If you have the larger number of regional record, you no need to go for the FINSIM simulation itself. So the simulations are heavily affected by subfault size consider. So that means if you take a bigger subfault and smaller subfault, depends upon that your simulations will be differ. So this is the limitation of this model. So the EXSIM, so EXSIM Mortadella and Atkinson 2004. So in order to avoid the limitations in the FINSIM model, so the overcoming limitation in the FINSIM, so the Mortadella and Atkinson introduce a concept of dynamic corner frequency. So that means that the corner frequency you can keep on changing, which will make a simulation independent of the subfault size. Okay, so now this model will overcome the subfault size kind of thing. So if FINSIM uses conservation of the total moment when the summed up all the subfault event with EXSIM works, and at conservation of the energy using the normalized velocity spectrum. Okay. So the duration of model does not depend upon the stress drop. Okay. So this also is another benefit of each subfault will be modeled as a point source. Okay, and then summation of the site interest will be done suitable time delay. You can see that the point source model was the origin. Okay, so where this mathematics and simulation concept has been expanded and studied in detail. So as on now the SMSIM models are the better one, which needs a good one, but this also before below magnitude 7 EXSIM and SMSIM does not make much difference. Above 7 earthquake you need to use a EXSIM, depends upon the place. So even now you can categorize that if you want to use simulation at peninsular India where you expect a moderate earthquake, so like the below 7.5 and 8 magnitude, you can go for the SMSIM, mostly 6, 6.5 and all you can easily create by the SMSIM model. But if you want to simulate earthquake at the Himalayan belt, okay, or North India where you expect a earthquake magnitude of 7 and above, so you cannot use SMSIM model, you should use the SMSIM model you cannot use, you can use a EXSIM model, okay, EXSIM model you should use in the North India. So this is the difference of making more understandable the engineering seismology part in the course. So this is the typical earthquake recorded data and synthetic ground motion data. So as I told you that the entire fault, okay, so is considered as a point source. So here again the entire fault divided as a different segment, each has been taken as a single record. So this is a single which is produces one time history, this is the multiple time history clubbed together and finally arrived this one. So this is basically the SMSIM, this is the SMSIM. So this is more suitable for the peninsular India, this is suitable for the North India above magnitude of 7, and but you need to have the source information which is required for the input. So this is how the simulations are done. So this is the typical earthquake where we have simulated in Indian University of Science. So as I told you that the simulation and getting a ground motion model itself a PhD topic. So in 2004 when I joined in the institute for the PhD, so I have been asked to work on the seismic microzonation of the Bangalore city, so where I started my research. So that time there was a Professor R.N. Iyengar, okay, he was one of the pioneer person in the engineering seismology in the country. So he was in the structural group, so I was working with Professor T.G. Sitaram, so who was my PhD guide come mentor. So we are in actually soil mechanics engineering or geotechnical engineering group. So with Professor R.N. Iyengar there was a student called Raghukant. Okay, so now Raghukant is a faculty at IIT Madras. Okay, so I am faculty at IISc. So he was actually doing the stochastic simulation model for Indian peninsular region and try to develop a ground motion prediction equation. So that was his PhD work actually. Why I want to tell you that the simulation of the ground motion model itself a PhD work. Okay. So then I also try to understand, okay, so since he is working on the simulation of ground motion, I need acceleration time history for the site response analysis, which we have discussed what is the time history and response spectrum. No? So in order to get a response spectrum time history at the ground surface, I need acceleration time history at the bedrock to give us the input. So in that purpose, I start learning the simulation of the data. So finally, I have been success in simulating the SMSIM model, using SMSIM model and regional data which is studied by somebody else. I simulated the first acceleration time history for Bangalore region, we can say. Some of my papers you can find which is published in 2006 and 7 on seismic hazard analysis and all. Then I started working on this region, followed by my next student Abhishek Kumar, who is a faculty at IIT Guwahati. So also done simulation for the Lucknow region. So then followed by the recent my student Ketan Bajaj, who has done extensive simulation by deriving a regional source path parameters using the recorded earthquake in India. That was one of the highlight. So we compiled data after my PhD. As I became a faculty, I compiled all the acceleration time history from the different part of India and tried to estimate the parameters, source and path parameters, which we have discussed, Q, K and stress drop and then the attenuation characteristics, different part using the data, and then using that we simulate a earthquake ground motion for Himalayan region for different earthquake and peninsular Indian different earthquake. And this is the typical example how our simulations are matching well with the recorded data. This is actually 1988. So India Bangladesh earthquake. Okay, so where you can see the black one is actually recorded data. So the red one is synthetically simulated data by us. Okay, you can see how quite it matches well. So as I told you that the source parameter, path parameters all contribute that. So we had made even some parametric studies to fix the particular earthquake source parameter when it is not available. So that means we alter the parameter and try to match exactly 2-3 record of the same earthquake. Once it is recorded well, the same parameters has been used to simulate at a different distance and so magnitude in the same source. That was the process we have taken up. You can see a spectrum comparison. So it's a very good, nice, the well comparison of the spectrum basically for this particular earthquake. This is 1991 Uttarakasi earthquake. So again the actual data and recorded data. So here also you can see the comparison of the spectrum, which is very well acceptable. So part of simulating like this a large number of earthquake in North India and South India. So finally we have come up with the ground motion prediction equation for North India, South India very recently, which is robust, okay, with respect to magnitude. It is applied to the wide range of magnitude and wide range of distance, which is not possible applicable in the previously generated GMP so far. So those who are interested on simulation and development of ground motion prediction equation, you can refer those research papers which will be useful. Okay, so you can go through and get, if you are interested to continue your research or want to do some contribution, basically you can work on this area, you can approach me. Okay, so this is how the ground motion simulation data are useful and which will be generated for any earthquake by knowing the regional parameters. Okay, so with this we will close the today class. Okay, so next class we will continue about the what is mean by the ground motion prediction equations. Okay, how it is useful, what is the state of art knowledge in the ground motion prediction equation, the next class. So thank you for watching this video. I look forward in the next class. So thank you very much. Bye bye.